So far we have discussed about the scale invariant function and some basic type of scale invariant function and some example of scale invariant function. Here we will discuss in more detail about how to detect the extrema point or extrema detection in scale and space, or we call it key point localization. We say it we will be discussing in more detail about the scale invariant function. And here in extrema detection we will find points that are local extrema. This means we need to find or identify points that are best representation of a region of the image in different scales. To locate these key points or interest points, we iterate over each pixel and compare it with all its neighbor. In other words, we want to find a robust maxima or minima in both space and scale. We have been talking about scale in space a lot, but the idea is as shown in figure. Here I have an image, and I have an image, and we could filter that image again and again, and some more again, and we could think of it as a cursor and cursor scale, and we have some point in that image and think of that as having neighbors on the left and right in an image itself. Like I have this point and I have its neighbor in its left, right, and up and down. Similarly, and this image and this neighborhood represents the space, and we can also think of that point having neighbors in up and down in this scale. Like this point has its neighbor in space. Space means the neighborhood in the image itself, and it may have the neighbor in the scale. Like it may have a scale up, it may have its neighbor in up and down scale, and this scale is represented by the blurrier versions of the image itself. And then this neighborhood in its image itself and the neighborhoods in the up and down scale it's represented as a scale space. Now, a specific way of using this scale space was suggested by David Law in Shift paper, that scale invariant feature transform. We will discuss in more detail about in our subsequent lectures. But at that point there was a specific suggestion to do this using the difference of Gaussian pyramid. What that means is we do it at different scales and over the space, and find the maximum value in all of those. And while doing it, some things sometimes we find only the edges, and what we have to do is we have to eliminate those edge points, because we know that the Laplacian and Gaussians they were introduced to find edge points. As Harris said, that edges are not good for finding specific locations, so we want it to be more like a corner. So basically what we want is we want to find points that have extrema values and they are thresholded, that they are extreme enough, and then make sure they are not the edges. So here is the particular way to do it. Basically what we do is we take an image. Here we have got image, here we have got image, and what we do is we deal this image with an octave, and here we have the first half octave and next octave. The octave means like the octave, we make the image like the octave represents the doubling the size, like the octave represents size, and this scale represents the blurrier version or the smoothness of the image. So in each octave we make the image blurrier and blurrier by Gaussian kernel. Then in next octave we reduce down the image to its the half of the size and make it blurrier and blurrier. We can see here in first octave we have a image and we make it blurrier and blurrier in its scale, and in we can see here the next octave, and this octave also consists of different scales, but this octave represents the scaled down image, and we call it not the scale down, we call it the half of its size. Here we should be clear that here the scale represents the blurrier version, and the octave represents the size of the image. So once we get this scale and octave, what we do is we subtract these images and find the difference of Gaussian. Here we can see I have the image at the different scale, and this scale is changed by the different sigma value, and once we get this different scaled version of image, we take the difference and we get the difference of Gaussian. Similarly, here in the next octave we also blur the image and get the difference of Gaussian. And here we can see the example. We can see here, then with each of these Gaussian images we are going to compare a pixel, and we compare this marked pixel. Here we can see this is the marked pixel, and what we do is we compare this pixel to each of its 8 neighbors in the same space. Like this pixel is compared. Once we get the difference of Gaussian, we compare this with the pixel around its neighbors in space, and it's 9 neighboring pixel in scale, like above it. We compare this pixel with this 8 neighbors and 9 neighbors below the scale and 9 neighbors above the scale, and if the pixel is maximum of those neighbors, then it's taken as a extrema. And here is an example. Here we have a picture of Einstein, and we can see that picture in the different octaves. Here this picture in octave 1, we can say it 1 octave, another octave, and another octave, and we can see here the image in 4 different octaves and 5 different scales. And what we do is we out in half and out in half and half, we can see the octave, and we can see it go from sharper to blurrier and blurrier to blurrier, and we can subtract these two images and get the difference. We can see here, like here I can subtract these two images and get the difference of Gaussian, and again I have a blurrier version, and again I get the difference of Gaussian and find the difference of Gaussian, and like this, and we get the difference of Gaussian at different scale and at the different octaves. And then what we do is we can take each pixel in one of these image and compare its neighbor in space and scale, and when we do all of that, we can find the extrema, and it looks like that. Like once we get this difference of Gaussian, then we take one pixel and compare that with its neighbor in scale and space that we have seen before,